At the dawn of the 20th century, physics appeared to be a nearly complete description of nature. The laws formulated by Newton, refined through Maxwell's equations, and tested in countless experiments, seemed capable of explaining everything from the motion of planets to the behavior of electricity and light. Matter was assumed to be continuous, predictable, and fully governed by deterministic rules. Yet beneath this surface of confidence, cracks were already forming. Certain experimental results refused to align with classical expectations, and nowhere was this failure more disturbing than in the attempt to understand the atom itself. The atom, long thought to be the smallest indivisible unit of matter, had already been shown to possess internal structure. Experiments by J. Thomson revealed the existence of electrons, negatively charged particles far smaller than atoms. This discovery forced scientists to imagine atoms not as solid spheres, but as systems made of smaller components. Thomson proposed a model in which electrons were embedded in a diffuse positive charge, often compared to raisins in a pudding. While this idea accounted for some electrical properties, it failed to explain how atoms emitted light or why they behaved with such remarkable stability. The situation became even more complex when Ernest Rutherford conducted his famous gold foil experiment. By firing alpha particles at thin sheets of gold, Rutherford discovered that most particles passed straight through, but a small number were deflected at large angles. This observation led to a shocking conclusion: the atom is mostly empty space, with nearly all its mass and positive charge concentrated in a tiny central nucleus. Electrons must therefore exist outside this nucleus, moving around it in some manner. The atomic picture suddenly resembled a miniature solar system, with electrons orbiting a dense core. At first glance, this nuclear model seemed like a triumph. It explained scattering experiments and gave atoms a clear internal structure. However, it immediately ran into a devastating problem when examined through the lens of classical physics. According to classical electrodynamics, any charged particle that accelerates must emit radiation. An electron moving in a circular orbit is constantly accelerating because its direction is continuously changing. This meant that orbiting electrons should lose energy all the time. As they radiated energy away, they would spiral inward, collapsing into the nucleus in a tiny fraction of a second. If this were true, atoms would be fundamentally unstable. Matter could not exist in a persistent form. Solid objects, living beings, and even the air itself would disintegrate as electrons crashed into nuclei. Yet the universe was clearly not behaving this way. Atoms were stable. Matter endured. This contradiction was not a minor technical issue, it was a direct clash between theory and reality. Classical physics, despite all its successes, could not explain why atoms do not self-destruct. Another major failure appeared in the study of light emitted by atoms. When elements are heated or energized, they glow. Classical theory predicted that atoms should emit light across a continuous range of wavelengths, much like a hot piece of metal glowing red, and then white as its temperature increases. Instead, experiments showed something entirely different. Each element produced a unique pattern of sharp spectral lines at very specific wavelengths. Hydrogen, the simplest atom, displayed a beautifully ordered series of lines that could be measured with extreme precision. Classical physics had no explanation for why only certain colors appeared and why those colors followed such regular mathematical patterns. Attempts to fix these problems within the classical framework only led to deeper confusion. Physicists tried modifying electron motions, adjusting charge distributions, and introducing ad hoc assumptions, but none of these efforts solved the core issues. The stability problem and the spectral problem were tightly linked, and neither could be resolved without abandoning some of the most cherished assumptions about how nature works. At the same time, other experiments were already hinting that energy itself might not be continuous. Max Planck, while studying blackbody radiation, discovered that he could only explain experimental data by assuming that energy is exchanged in discrete packets, later called quanta. Albert Einstein extended this idea to light itself, proposing that light sometimes behaves as if it consists of particles, now known as photons. These ideas were radical and deeply unsettling, but they worked. They suggested that at microscopic scales, nature might operate according to rules very different from classical intuition. Despite these breakthroughs, the atom remained an unsolved mystery. There was no unified picture that explained both atomic structure and atomic radiation. The crisis in physics was not just about missing details, it was about the apparent breakdown of the entire conceptual framework that had guided science for centuries. Determinism, continuity, and smooth motion no longer seemed sufficient to describe reality at its smallest scales. It was into this atmosphere of uncertainty and intellectual tension that Niels Bohr entered. Trained in classical physics but deeply aware of its limitations, Bohr recognized that the atomic problem could not be solved by minor adjustments. The contradictions were too fundamental. If atoms existed and were stable, then the laws governing them had to be different in kind, not merely in degree, from classical laws. Bohr's insight was shaped by the growing evidence that energy quantization was not a mathematical trick, but a real feature of nature. Instead of asking how electrons could orbit the nucleus without radiating, Bohr asked a more daring question. What if electrons are simply forbidden from radiating in certain states? This was not something classical physics could justify, but Bohr was willing to accept it if it matched reality. The crisis of classical physics, therefore, was not a sudden collapse but a slow realization that deeply held assumptions were no longer universal. The atom exposed the limits of human intuition, revealing that the rules governing everyday objects cannot be blindly extended to the microscopic world. Stability, radiation, and structure all demanded new principles. This moment marked a turning point in the history of science. Physicists were forced to confront the possibility that nature is layered, with different laws applying at different scales. The atomic problem was not merely a puzzle to be solved, it was a signal that the foundations of physics itself needed to be rebuilt. Bohr's work emerged directly from this crisis. Without the failure of classical physics to explain atomic stability and spectra, there would have been no need for such a radical rethinking of matter. The inadequacy of existing models was not a weakness of science, but its strength. By exposing contradictions, experiments pushed theory beyond its comfort zone and opened the door to a deeper understanding of reality. In this sense, the crisis of classical physics was not the end of an era, but the beginning of a new one. It forced scientists to abandon the idea that the universe must conform to human intuition. Instead, intuition had to be reshaped to fit the universe. The atom became the stage on which this transformation played out, revealing that beneath the apparent simplicity of matter lies a world governed by rules both strange and profoundly precise. As the implications of this crisis became clearer, physicists began to realize that the failure of classical ideas was not limited to a single experiment or anomaly. It was systemic. Every attempt to describe atomic behavior using continuous motion and classical radiation laws led to contradictions. The more precise the measurements became, the more obvious it was that atoms were obeying rules that had no place in 19th century physics. This growing tension created an intellectual environment in which radical ideas were no longer just acceptable, but necessary. One of the most unsettling aspects of the atomic problem was that classical physics worked extremely well at larger scales. The same equations that failed completely inside the atom could predict planetary motion, bridge stability, and electrical circuits with extraordinary accuracy. This raised a profound question. How could a theory be so successful in one domain and so catastrophically wrong in another? The answer, though not immediately obvious, lay in scale. Atoms were not simply smaller versions of familiar objects. They belonged to a different regime of nature altogether. The realization that scale matters in such a fundamental way was deeply uncomfortable. Classical physics was built on the assumption that laws are universal, applying equally to all sizes and energies. The atomic crisis shattered this belief. It suggested that nature does not operate under a single, seamless set of rules. Instead, different layers of reality may require different descriptions. This was not just a technical adjustment, it was a philosophical rupture. The spectral lines of hydrogen played a central role in reinforcing this conclusion. Their regularity was too precise to be accidental. Mathematical formulas developed purely from experimental observation, such as the Balmer and Rydberg formulas, could predict these lines perfectly, yet had no theoretical explanation within classical physics. These formulas worked, but no one knew why. This situation was deeply troubling for scientists who believed that understanding meant more than prediction. It required a coherent picture of underlying mechanisms. Classical models tried to imagine electrons moving in complex paths, vibrating, or oscillating in ways that might somehow restrict radiation to certain frequencies. But these attempts quickly collapsed under scrutiny. Any accelerating charge, no matter how complicated its motion, should radiate across a broad range of frequencies. There was no way to selectively turn off radiation at most wavelengths while allowing it at only a few discrete ones. The very sharpness of spectral lines directly contradicted the smoothness inherent in classical motion. Another issue was the apparent discreteness of atomic behavior. Atoms absorbed energy only at specific frequencies. They emitted energy only at specific frequencies. There was no gradual transition, no partial absorption, no smooth sliding from one state to another. This behavior was alien to classical thinking, which assumed that systems respond continuously to forces and energy inputs. The atom seemed to act more like a system with allowed and forbidden states, rather than one governed by smooth trajectories. This discreteness extended beyond light. Chemical behavior also hinted at underlying quantum structure. The periodic table revealed repeating patterns in atomic properties that could not be explained by classical electron arrangements. Elements exhibited distinct valences reacting in fixed numerical ratios. While chemistry had developed powerful empirical rules, their deeper explanation was missing. Once again, atoms appeared to follow strict internal constraints that classical physics could not justify. The crisis therefore expanded beyond physics into chemistry and material science. Understanding why matter has the properties it does required understanding atoms, and understanding atoms required abandoning classical assumptions. The atom became the focal point of a broader scientific revolution. Many physicists initially resisted this conclusion. The success of classical physics had shaped not only their calculations, but their intuition about reality. Accepting that electrons could behave in ways that defied classical motion felt like surrendering rationality itself. Some hoped that a more sophisticated classical model would eventually resolve the contradictions. Others suspected that experimental errors or incomplete data were to blame. Yet as experiments became more refined, the discrepancies only grew sharper. What made the situation particularly difficult was the lack of a clear alternative framework. Quantum ideas existed in fragments. Planck's energy quanta explained blackbody radiation, but Planck himself viewed quantization as a mathematical trick rather than a statement about reality. Einstein's light quanta explained the photoelectric effect, but even Einstein was uneasy with the implications. These ideas solved specific problems, but they did not yet form a coherent picture of atomic structure. The atom thus sat at the crossroads of old and new physics. Classical ideas failed, but quantum ideas were incomplete. This liminal state created both frustration and opportunity. It forced physicists to confront the possibility that nature is fundamentally probabilistic, discrete, and constrained in ways that defy everyday experience. In this context, the failure of classical physics was not merely negative. It served as a guide, pointing toward the kinds of assumptions that had to be abandoned. Continuous energy, deterministic trajectories, and universal classical laws all became suspect. The atom was teaching physicists what it could not be, even before revealing what it truly was. This process of learning through failure is a recurring theme in scientific progress. The breakdown of classical atomic models was not due to sloppy thinking or incomplete effort. It was the result of pushing a powerful theory beyond its domain of validity. Classical physics had reached its natural limit, and the atom lay beyond that boundary. The recognition of this limit required intellectual humility. It demanded that physicists accept that even the most successful theories are provisional. They are maps, not the territory itself. When the map no longer matches the landscape, it must be redrawn. The atomic crisis made this lesson unavoidable. As the 20th century progressed, it became increasingly clear that the atom was not an isolated exception. Similar failures appeared in other areas involving very small scales or very high energies. These failures reinforce the idea that classical physics is an approximation valid only under certain conditions. At everyday scales, quantum effects average out, giving the illusion of continuity and determinism. At atomic scales, however, these effects dominate. This understanding transformed the crisis into a doorway. The atom was no longer seen as a problem threatening the foundations of physics, but as a clue to a deeper layer of reality. The challenge was no longer to save classical physics at all costs, but to discover the principles that replace it where it fails. Niels Bohr's contribution would soon provide one of the first coherent steps through that doorway. But even before his model was proposed, the crisis itself had already reshaped scientific thinking. It taught physicists that intuition must be guided by experiment, not the other way around. It revealed that nature does not owe us simplicity or familiarity. Instead, it offers consistency, even if that consistency requires ideas that feel strange or counterintuitive. The failure of classical physics to explain atomic behavior thus stands as one of the most productive failures in the history of science. It forced a re-examination of fundamental concepts such as energy, motion, and stability. It showed that understanding the universe sometimes requires letting go of deeply held beliefs and embracing uncertainty. In retrospect, the crisis was not a sign that physics was broken, but that it was alive. The atom challenged existing theories precisely because it contained new information about how the universe works. By refusing to conform to classical expectations, it pushed science forward. This moment marks the threshold between two worldviews. On one side lies the classical universe, smooth, predictable, and continuous. On the other lies the quantum universe, discrete, probabilistic, and constrained by rules that defy common sense yet produce astonishing order. The inability of classical physics to explain the atom made it clear that crossing this threshold was unavoidable. Before any new model could succeed, this failure had to be fully acknowledged. Only by accepting that the old framework was insufficient could physicists begin to build a new one. The crisis of classical physics was therefore not just the background to Bohr's work, it was its essential precondition. Without this crisis, the revolutionary explanation of how the atom really works would never have been possible. When Niels Bohr began to think seriously about the structure of the atom, he was fully aware that the existing picture was internally inconsistent. The nuclear model placed electrons in motion around a dense positive nucleus, yet classical physics insisted that such motion could not persist. Instead of trying to repair this contradiction using familiar ideas, Bohr made a decisive conceptual leap. He proposed that the motion of electrons inside atoms is governed by rules that simply do not apply anywhere else in nature. This was not an incremental improvement, but a fundamental change in how atomic motion itself was understood. The most radical element of Bohr's thinking was the idea that electrons are restricted to certain specific motions. Rather than allowing electrons to orbit the nucleus at any distance or with any energy, Bohr suggested that only particular orbits are permitted. Each of these orbits corresponds to a precise energy value, and electrons can exist only in these discrete states. All other possibilities are forbidden by nature. This assumption directly contradicted classical mechanics, where a particle can, in principle, have any energy and follow infinitely many possible paths. Bohr did not arrive at this idea arbitrarily. He was guided by experimental evidence and by the emerging concept of quantization introduced by Planck and Einstein. Energy exchange at the atomic level appeared to occur in fixed packets rather than continuously. Bohr extended this principle inward, into the very structure of the atom. Instead of energy being quantized only during emission or absorption of light, Bohr proposed that the allowed motions of electrons themselves are quantized. In this picture, an electron moving in one of the allowed orbits does not lose energy, no matter how long it remains in motion. This single assumption resolved the most devastating problem of the nuclear atom. Electrons no longer spiral into the nucleus because the laws of nature do not permit them to occupy intermediate states. As long as an electron stays in an allowed orbit, it is perfectly stable. Radiation occurs only when the electron transitions between these states, not while it remains within one. To justify which orbits are allowed, Bohr introduced a specific condition on angular momentum. He proposed that the angular momentum of an electron in orbit around the nucleus must be an integer multiple of a fundamental constant, related to Planck's constant. This condition had no basis in classical mechanics, yet it provided a clear mathematical rule that selected certain orbits and excluded all others. With this rule, the size, energy, and stability of atomic orbits could be calculated precisely. The consequences of this idea were extraordinary. From a simple quantization condition, Bohr was able to derive exact expressions for the energies of electrons and hydrogen. These energies matched perfectly with values inferred from spectroscopy. The mysterious numerical regularities observed in hydrogen's spectral lines suddenly had a physical explanation. They were not accidental patterns, but direct reflections of the allowed energy levels inside the atom. This marked a profound shift in scientific reasoning. Instead of asking how electrons move continuously under forces, physicists were now asked to accept that motion itself is constrained by abstract rules. The atom was no longer a miniature mechanical system obeying familiar laws. It became a quantized structure defined by discrete possibilities rather than smooth variation. Bohr's allowed orbits were not meant to be visualized as literal tracks like planetary paths. Although the language of orbits was used, Bohr emphasized that these were symbolic representations of allowed states rather than actual trajectories in the classical sense. The electron's behavior could not be fully described using ordinary concepts of position and motion. What mattered was not where the electron was at every moment, but which energy state it occupied. This way of thinking required a significant adjustment in intuition. Classical physics had trained scientists to believe that understanding meant picturing motion in space and time. Bohr's model challenged this belief. It suggested that understanding at the atomic level might require accepting rules that cannot be fully visualized. Mathematical consistency and agreement with experiment became more important than mechanical imagery. The idea of quantized orbits also introduced a new notion of atomic individuality. Each atom possessed a unique set of allowed energy levels determined by its nuclear charge. This explained why different elements emit different spectral lines and exhibit distinct chemical behaviors. Atomic identity was no longer an emergent property of bulk matter, but a direct consequence of quantized internal structure. Another important implication was the introduction of forbidden states. In classical physics, if a system can have one energy, it can usually have energies arbitrarily close to it. Bohr's atom rejected this continuity. There were gaps between allowed energy levels that electrons could never occupy. These gaps were not due to instability or external forces, they were intrinsic features of nature. This idea of forbidden regions would later become central to quantum mechanics and solid-state physics. The success of Bohr's model did not lie in its realism, but in its predictive power. It correctly described the size of the hydrogen atom, the energies of its spectral lines, and the conditions under which light is emitted or absorbed. These achievements demonstrated that quantization was not a mathematical convenience, but a physical necessity. The atom behaved as if it were governed by a set of rules fundamentally different from those of classical motion. Despite its success, Bohr was acutely aware of the model's limitations. It applied cleanly only to hydrogen and hydrogen, like ions, When extended to atoms with more electrons, the simplicity broke down. The interactions between electrons introduced complexities that the orbit picture could not handle. Nevertheless, this did not diminish the importance of the core idea. The quantization of allowed states was the key insight, even if the orbital imagery would later be replaced. Bohr's approach also carried deep philosophical implications. It suggested that nature imposes constraints that are not derived from underlying mechanical causes, but are instead fundamental principles. The allowed states simply exist, and particles must conform to them. This idea challenged the reductionist hope that all phenomena could be explained in terms of continuous motion and force. The introduction of quantized orbits marked the first time that physicists deliberately abandoned classical laws at the microscopic level while retaining them at larger scales. This selective application of laws was revolutionary. It implied that physical theories are not universally valid across all domains, but have limits defined by scale and context. This shift required a new attitude toward theory building. Rather than insisting on consistency with classical intuition, Bohr prioritized consistency with experimental facts. If experiments demanded quantization, then quantization had to be accepted, even if it lacked a deeper explanation at the time. This pragmatic approach would later become a defining feature of quantum theory. The idea of discrete energy levels also transformed the concept of measurement. Observing an atom was no longer a passive act. Measurements could induce transitions between states, causing the atom to emit or absorb energy. The act of observation became intertwined with the behavior being observed. This insight hinted at deeper issues that would later be explored in full quantum mechanics. Bohr's model demonstrated that simplicity at a fundamental level does not necessarily mean familiarity. A few simple rules could generate complex and counterintuitive behavior. The atom, though governed by strict constraints, could exhibit a rich variety of phenomena depending on how its states were occupied and how transitions occurred. In retrospect, the notion of quantized orbits can be seen as a bridge between classical and quantum thinking. It retained elements of classical imagery while embedding them within a non-classical framework. This hybrid nature made the model accessible while still revolutionary. It allowed physicists to gradually adjust their thinking rather than abandoning all familiar concepts at once. The enduring legacy of this idea lies in how it redefined what it means for something to be allowed in nature. Possibility itself became quantized. Not everything that can be imagined is permitted. The universe operates by selecting specific options and excluding all others with absolute precision. This insight laid the groundwork for all later developments in atomic and quantum physics. Even though the picture of electrons in fixed orbits would eventually be replaced by wave functions and probability distributions, the underlying principle remained intact. At the deepest level, systems exist in discrete states governed by quantized rules. By proposing that electrons can occupy only certain allowed states, Bohr provided the first coherent explanation of atomic stability and spectral structure. More importantly, he introduced a new way of thinking about physical reality, one that accepts limitation, discreteness, and abstraction as fundamental features of nature rather than imperfections of theory. As this new picture of the atom took shape, its implications reached far beyond the immediate problem of stability. The idea that electrons are confined to specific allowed states fundamentally altered how physicists understood motion itself. In classical thinking, motion is continuous and governed by forces that act smoothly over time. In Bohr's atomic picture, continuity was replaced by permission. An electron could exist only where the rules allowed it to exist, and nowhere else. Motion between these states was not gradual but abrupt, occurring in sudden transitions that defied everyday intuition. This raised a profound question about causality. In classical mechanics, if the position and velocity of a particle are known, its future motion can be predicted exactly. In the atomic realm described by Bohr, knowing the current state of an electron did not determine how or when it would change states. The transition itself was not described as a trajectory or a force-driven process, it simply happened. This absence of a detailed mechanism was unsettling to many physicists, yet it matched experimental reality with remarkable precision. The quantized states of the atom also introduced a new understanding of energy conservation. Energy was still conserved, but only in discrete exchanges. When an electron jumped between states, the energy difference appeared as a photon with a precise frequency. There was no partial photon, no gradual emission. The all or nothing character of these transitions reinforced the idea that atomic processes are fundamentally discontinuous. Conservation laws survived, but their expression changed in subtle and profound ways. Bohr's model also redefined the meaning of equilibrium. In classical systems, equilibrium often involves a balance of forces. In the atom, equilibrium took on a new meaning. A stable atomic state was not one in which forces canceled out, but one in which the electron occupied an allowed energy level. Stability was no longer dynamic balance, but rule-based permission. This shift in perspective had deep consequences for how physicists thought about stability in other microscopic systems. As experimental techniques improved, the quantized nature of atomic states became increasingly evident. Spectral lines could be measured with extraordinary accuracy, and their agreement with Bohr's predictions left little doubt that the core idea was correct. The fact that such a simple rule could produce such precise agreement was both exhilarating and disturbing. It suggested that nature might be governed by principles that are simple in form, but radically different in spirit from classical laws. At the same time, cracks began to appear in the orbital picture itself. The more carefully physicists examined atomic behavior, the harder it became to maintain the idea of electrons as tiny particles following well-defined paths. Certain spectral features could not be fully explained, and interactions involving multiple electrons resisted simple treatment. These difficulties hinted that the language of orbits was only an approximation, a temporary scaffold, rather than a final structure. Bohr himself was keenly aware of this. He emphasized that the orbits were not observable entities. No experiment could directly reveal an electron circling the nucleus along a precise path. What experiments revealed were energy levels and transitions between them. The orbits were a way of organizing these facts, not a literal picture of reality. This distinction was crucial. It marked a departure from the belief that theoretical models must correspond directly to visualizable mechanisms. This attitude paved the way for a new philosophy of physics. The value of a theory was no longer judged by how intuitively it could be pictured, but by how accurately it connected observable quantities. Bohr's willingness to abandon visual realism in favor of abstract rules was a decisive step toward modern quantum mechanics. The quantization of atomic states also reshaped the understanding of measurement. Measuring the energy of an atom meant determining which state it occupied. But any interaction strong enough to reveal this information could also change the state itself. The boundary between observation and disturbance became blurred. This insight, though not fully developed in Bohr's early work, was implicit in the idea of state transitions and would later become central to quantum theory. Another important consequence was the emergence of probability as a fundamental concept. While Bohr's original model did not explicitly use probability, it opened the door to probabilistic thinking by abandoning deterministic trajectories. If the exact motion of electrons could not be specified, then predictions would necessarily be statistical. Later developments would formalize this idea, but its roots lay in the rejection of classical determinism at the atomic scale. The influence of quantized atomic states extended into chemistry. Chemical bonds, valence, and reactivity could now be understood in terms of electrons occupying specific energy levels. Although Bohr's model was too simple to handle complex atoms in detail, it provided the conceptual foundation for later theories of electronic structure. Chemistry, once largely empirical, began to acquire a deeper theoretical basis grounded in quantum principles. The idea of forbidden and allowed states also found echoes in other areas of physics. In solids, for example, electrons occupy energy bands separated by forbidden gaps. The behavior of conductors, insulators, and semiconductors depends directly on these quantum constraints. Though these developments came later, they trace their intellectual lineage back to the insight that not all energies are permitted. Bohr's work also influenced how physicists thought about explanation itself. In classical physics, explaining a phenomenon usually meant reducing it to simpler mechanical processes. In the atomic domain, explanation took on a different character. It involved identifying the rules that govern what is possible and impossible. This rule-based explanation did not satisfy everyone, but it proved extraordinarily powerful. The resistance to these ideas gradually weakened as their success became undeniable. What initially seemed like an arbitrary assumption revealed itself as a reflection of how nature actually behaves. The quantization of atomic states was not imposed by theory, it was demanded by experiment. This realization helped physicists accept that their intuitions, shaped by macroscopic experience, were not reliable guides at the microscopic level. Over time, the orbital picture would give way to a more sophisticated understanding involving waves, probability amplitudes, and mathematical operators. Yet the central lesson remained unchanged. The behavior of electrons is constrained by quantized states, and transitions between these states define the interaction between matter and energy. The specifics of the model evolved, but the principle endured. Bohr's introduction of quantized orbits thus represents more than a historical curiosity. It marks a turning point in the human attempt to understand nature. It showed that reality at its deepest level may not be continuous, deterministic, or easily visualized. Instead, it may be structured by abstract rules that select certain possibilities and exclude others with absolute authority. This insight reshaped not only physics, but the scientific worldview as a whole. It taught scientists to trust experimental evidence even when it conflicts with intuition. It encouraged the development of new mathematical tools and new philosophical frameworks. Most importantly, it revealed that the universe is far stranger and more subtle than classical thinking had ever imagined. By accepting that electrons can occupy only certain allowed states, Bohr provided a framework that explained atomic stability, spectral regularities, and the discrete nature of energy exchange. In doing so, he transformed a collection of puzzling observations into a coherent picture. The atom was no longer a source of contradiction, but a gateway to a deeper understanding of the laws that govern reality itself. One of the most striking mysteries of the atomic world before the 20th century was the behavior of light emitted by matter. When gases were heated, electrified, or otherwise energized, they did not glow in a smooth, continuous rainbow of colors. Instead, they produced sharp, narrow lines at very precise wavelengths. Each chemical element had its own unique pattern, like a barcode written in light. These patterns were measured with increasing accuracy, yet no one could explain why nature behaved this way. Classical physics predicted something entirely different, and the gap between theory and observation grew wider with every experiment. According to classical ideas, atoms were expected to radiate energy continuously. An accelerating charge, such as an electron moving within an atom, should emit electromagnetic waves across a broad range of frequencies. If electrons could move with arbitrary energies, then the light emitted by atoms should also span a continuous spectrum. This expectation worked reasonably well for large, hot objects like glowing metal, but it failed completely for isolated atoms. The observed sharp lines were too precise, too stable, and too reproducible to be dismissed as experimental artifacts. Long before a theoretical explanation existed, experimentalists uncovered mathematical regularities in these spectral lines. In hydrogen, the simplest atom, the visible lines followed a simple numerical pattern described by the Balmer formula. Later, this pattern was extended to other regions of the spectrum by the Rydberg formula. These equations could predict the wavelengths of spectral lines with extraordinary accuracy, yet they offered no physical explanation. They were empirical rules, not understanding. Physicists knew how to calculate the lines, but not why they existed. This situation was deeply unsatisfying. Science aims not only to predict but to explain. The spectral lines seemed to be telling a story about the internal structure of atoms, but the language of classical physics could not translate it. Attempts to model electrons as oscillating charges or complex mechanical systems failed because they still implied continuous radiation. No classical mechanism could produce only a discrete set of frequencies and forbid all others. The breakthrough came with the realization that light emission is not a continuous process, but a result of sudden changes within the atom. In the new atomic picture, electrons do not gradually lose energy as they move. Instead, they occupy stable states with fixed energies. Light appears only when an electron changes from one state to another. The frequency of the emitted light is determined not by the details of the electron's motion, but by the difference in energy between the two states involved. This idea transformed the interpretation of atomic spectra. Each spectral line corresponds to a specific transition between two energy levels. The reason only certain lines appear is because only certain energy levels exist. The atom acts like a finely tuned instrument that can play only specific notes. The gaps between energy levels determine which notes are possible and which are forbidden. Light is not produced by continuous motion, but by discrete jumps. In hydrogen, this explanation worked with remarkable precision. By calculating the allowed energy levels of the electron, it became possible to predict exactly the wavelengths of all observed spectral lines. The Balmer and Rydberg formulas were no longer mysterious numerical coincidences. They emerged naturally from the structure of the atom itself. What had once seemed like an arbitrary pattern was revealed to be a direct reflection of atomic order. This new understanding also explained why different elements produce different spectra. Each element has a nucleus with a different electric charge, which alters the allowed energy levels of its electrons. As a result, the energy differences between levels are unique for each element. When electrons transition between these levels, they emit or absorb light at characteristic frequencies. Atomic spectra thus became fingerprints of elements rooted in their internal structure rather than superficial properties. The concept of electron transitions also clarified the relationship between absorption and emission. When light of a specific frequency passes through a gas, atoms can absorb it only if the energy of the light matches exactly the energy difference between two allowed states. The electron then jumps to a higher energy state. Light of any other frequency passes through unaffected. This explains why absorption spectra consist of dark lines at the same positions as emission lines. Emission and absorption are two sides of the same process, governed by the same energy structure. This interpretation introduced a radical departure from classical causality. In classical physics, radiation is emitted because a charge is accelerating, and the frequency of radiation depends on the details of that motion. In the atomic picture, radiation is emitted because a transition occurs, and the frequency depends only on energy differences. The path taken by the electron during the transition is not described. The process cannot be visualized as a continuous motion in space and time. It is an event rather than a trajectory. This raised deep conceptual questions. How does an electron move from one state to another without passing through intermediate states? What happens during the transition itself? Early atomic theory did not provide answers to these questions. It simply stated the rules governing initial and final states and left the transition as an unexplained process. This lack of a detailed mechanism was troubling, yet it was unavoidable. Every attempt to force a classical picture onto the transition led to contradictions. Despite these conceptual difficulties, the success of the transition-based explanation was undeniable. It accounted for the sharpness of spectral lines, their precise frequencies, and their dependence on atomic structure. It also explained why atoms in stable states do not radiate energy. As long as an electron remains in a fixed energy state, no light is emitted. Radiation appears only when the atom changes state. This resolved the long-standing conflict between atomic stability and classical electrodynamics. The idea of discrete transitions also shed light on the intensity of spectral lines. The brightness of a line depends on how often a particular transition occurs. Factors such as temperature, excitation method, and atomic environment influence how many electrons occupy higher energy states and how frequently they drop to lower ones. While early models could not calculate these probabilities in detail, the qualitative understanding was clear. Spectral intensity reflects the population and behavior of atomic states, not continuous radiation. This framework transformed spectroscopy from a descriptive science into a diagnostic tool. By analyzing spectral lines, scientists could infer the energy structure of atoms, identify elements in distant stars, and measure physical conditions in remote environments. The light emitted by atoms became a messenger carrying information about the microscopic world across vast distances. The transition-based explanation also reinforced the emerging view that energy exchange at the atomic level is quantized. Light itself appeared not as a continuous wave emitted gradually, but as discrete packets associated with specific transitions. This idea aligned naturally with the concept of photons and strengthened the case for a fundamentally quantum description of light and matter. As experimental techniques improved, the agreement between predicted and observed spectral lines became even more precise. Small deviations revealed subtle effects such as relativistic corrections and interactions between electrons and magnetic fields. While these details lay beyond the simplest atomic models, they confirmed rather than undermined the central idea. The basic structure of energy levels and transitions was correct, even if refinements were needed. The explanation of atomic spectra through electron transitions also had far-reaching implications for time and change in physics. Transitions appeared instantaneous, or at least not describable by classical time-dependent motion. This challenged the assumption that all physical processes unfold smoothly in time. At the atomic scale, change could be abrupt and discontinuous, yet still obey strict conservation laws. This insight forced physicists to rethink what it means to describe a process. Instead of tracking motion step by step, atomic theory focused on initial and final states and the rules connecting them. This shift in emphasis marked a profound change in scientific methodology. Description became less about visualization and more about abstract relationships between measurable quantities. The success of this approach encouraged its application to other systems. Molecular spectra, nuclear transitions, and later even particle physics adopted similar ideas. Systems were understood in terms of discrete states and transitions rather than continuous trajectories. The atomic spectrum became the prototype for a new way of understanding nature. Over time, the language used to describe these processes evolved. The idea of electrons jumping between orbits was recognized as a metaphor rather than a literal description. Later quantum mechanics replaced orbits with wave functions and energy eigenstates. Yet the essential insight remained unchanged. Light is emitted and absorbed because systems change between discrete energy states, and the frequency of light reflects those energy differences. This understanding resolved one of the deepest puzzles in physics and revealed an unexpected harmony between matter and radiation. The atom and light were no longer separate phenomena governed by unrelated laws. They were intimately connected through energy quantization. The spectrum of an atom became a direct window into its internal structure. In explaining atomic spectra, the concept of electron transitions did more than solve a technical problem. It demonstrated that nature, at its most fundamental level, communicates through discrete changes rather than continuous flow. It showed that precision and order can emerge from rules that defy everyday intuition. The sharp lines observed in a spectroscope were no longer mysterious marks on a screen. They were signatures of a deeper reality in which energy, matter, and light are bound together by quantized relationships. This realization marked a decisive step toward modern quantum theory. It taught physicists to listen carefully to what experiments were revealing even when the message conflicted with long-held beliefs. The explanation of atomic spectra through transitions transformed confusion into clarity and turned one of physics' greatest puzzles into one of its most elegant achievements. As this interpretation of atomic light became accepted, it began to reshape how physicists understood not only atoms, but the very nature of interaction between matter and radiation. Light was no longer seen as something continuously shaken loose from electrons by their motion. Instead, it emerged as a precise signal of change, marking the moment an atom rearranged its internal energy. Every photon carried a clear message: an atom has moved from one allowed state to another. This view gave light a new role, transforming it from a passive wave into an active participant in atomic processes. One of the most profound consequences of this idea was the realization that atoms are selective in how they interact with radiation. An atom does not respond to just any incoming light. It can absorb energy only if that energy matches exactly the difference between two of its allowed states. This selectivity explained why atoms can be transparent to most frequencies while strongly absorbing others. The atom behaves like a filter, responding only to very specific conditions dictated by its internal structure. This selectivity also clarified why atomic spectra are so stable and reproducible. The positions of spectral lines do not depend on how an atom is excited, but only on its internal energy levels. Whether hydrogen is heated, electrified, or exposed to ultraviolet radiation, the same set of lines appears. This stability reflects the fact that the energy levels themselves are fixed properties of the atom. External conditions may change how often transitions occur, but not where they occur. The sharpness of spectral lines was another key insight. Classical models struggled to explain why emitted light had such narrow frequencies. In the transition-based picture, sharpness arises naturally. Because energy levels are discrete and well-defined, the energy differences between them are equally well-defined. As a result, the emitted photons have very precise frequencies. Any broadening of spectral lines can be traced to secondary effects such as thermal motion or interactions with other atoms, not to uncertainty in the energy structure itself. This understanding also introduced a new way of thinking about time at the atomic scale. In classical physics, radiation is emitted continuously over time as energy gradually leaks away. In atomic transitions, emission is associated with an event rather than a process. While the detailed timing of a transition may involve probabilistic elements, the energy change itself is exact. This separation between when a transition happens and how much energy it involves was a subtle but important shift in thinking. The probabilistic aspect of transitions became increasingly important as experiments grew more refined. Atoms prepared in identical conditions did not all emit light at the same moment. Instead, emission occurred unpredictably, though with well-defined statistical patterns. This randomness was not due to ignorance or experimental imperfections. It appeared to be a fundamental feature of atomic behavior. While early models could not fully explain this randomness, they clearly indicated that determinism had limits at the microscopic level. The explanation of spectra through transitions also influenced how physicists thought about excitation and decay. When an atom absorbs energy and moves to a higher state, it does not remain there indefinitely. It eventually returns to a lower state, releasing energy in the process. The lifetime of an excited state became an important, measurable quantity. Short-lived states produced broad spectral lines, while longer-lived states produced sharper ones. This connection between time and energy hinted at deeper principles that would later be formalized in quantum mechanics. Another major implication was the universality of the transition concept. While hydrogen provided the simplest and clearest example, similar ideas applied to more complex atoms. Although calculating their energy levels was far more difficult, the basic principle remained valid. Complex spectra arose from a dense network of allowed states and transitions. Even when the details became intricate, the underlying logic did not change. This framework also extended naturally to molecules. Molecular spectra, with their vibrational and rotational features, could be understood as transitions between quantized molecular energy states. Once again, light revealed internal structure. Spectroscopy became a powerful tool not just for identifying elements, but for probing the arrangement and motion of atoms within molecules. The impact of this understanding reached far beyond laboratory physics. Astronomers used spectral lines to identify the composition of stars and galaxies, measure their temperatures, and determine their motion through space. The same transition rules that governed atoms on Earth applied across the universe. Light traveling for millions of years carried with it precise information about atomic processes occurring in distant environments. The success of the transition-based explanation also strengthened confidence in the broader quantum approach. It showed that abandoning classical continuity did not lead to chaos or arbitrariness. On the contrary, it revealed a deeper order, one expressed through exact relationships and strict constraints. Nature was not less lawful at the atomic scale, but lawful in a different way. At the same time, this success highlighted the limitations of visual models. The idea of electrons jumping between orbits was useful but incomplete. It served as a conceptual bridge, allowing physicists to connect observed spectra with atomic structure. Over time, it became clear that a more abstract description was needed, one that did not rely on classical images of motion. This realization paved the way for wave mechanics and a more complete quantum theory. Yet even as the language changed, the essence of the insight remained intact. Atomic spectra are not incidental features. They are direct expressions of quantized energy structure. Every line tells a story of change within the atom, governed by rules that are both simple and profound. The explanation of spectra through transitions also altered how scientists thought about explanation itself. It showed that understanding does not always mean tracing a process step by step in space and time. Sometimes it means identifying allowed states and the rules that connect them. This state-based understanding proved to be a powerful way of describing systems where classical motion breaks down. In the broader context of science, this shift marked a departure from mechanical thinking toward structural thinking. The focus moved from forces and trajectories to patterns and constraints. This change influenced not only physics, but other fields that adopted similar approaches to complex systems. Looking back, the mystery of atomic spectra can be seen as a turning point. It forced physicists to confront the inadequacy of classical ideas and to embrace a new conceptual framework. The solution did not come from adding complexity to old models, but from accepting a fundamentally different view of how nature operates. By explaining atomic light as the result of transitions between discrete states, physicists uncovered a unifying principle linking matter and radiation. This principle brought coherence to a vast range of phenomena and revealed an unexpected simplicity beneath apparent complexity. In the end, the sharp lines observed in atomic spectra were not just experimental curiosities. They were signposts pointing toward a deeper level of reality. Understanding them required a willingness to rethink basic assumptions about motion, energy, and change. That willingness transformed a long-standing puzzle into a cornerstone of modern physics and opened the path toward a fuller understanding of the quantum world. The question of why atoms are stable once stood as one of the most troubling mysteries in all of science. According to classical physics, stability at the atomic level should be impossible. Electrons are negatively charged particles, and the nucleus is positively charged. The attraction between them is strong, and classical electrodynamics adds a fatal consequence. Any charged particle that moves in a curved path must continuously radiate energy. An electron circling a nucleus is constantly accelerating, even if its speed is constant, because its direction is always changing. Classical theory therefore predicts that the electron should lose energy steadily, spiral inward, and crash into the nucleus in an extremely short time. If this were true, atoms could not exist, and neither could the material world. Yet atoms are extraordinarily stable. Matter persists for billions of years. This stability is not fragile or rare, it is universal. Every solid object, every living organism, and every star depends on it. The contradiction between theory and reality revealed that something deeply wrong existed in the classical description of atomic motion. Stability was not a small detail to be fixed later. It was the central fact that demanded explanation. The breakthrough came when stability was no longer treated as a consequence of forces balancing each other, but as a result of strict rules governing what electrons are allowed to do. In the new atomic picture, electrons are not free to exist at any distance from the nucleus or with any energy they please. Instead, they are confined to specific states, each associated with a precise energy. As long as an electron remains in one of these states, it does not radiate energy at all. This single assumption overturns the classical prediction of collapse. Stability, in this view, is not achieved dynamically but structurally. It is not that electrons are constantly losing energy and somehow being replenished. Rather, energy loss simply does not occur in these stable states. The laws of nature forbid it. An electron can remain in such a state indefinitely without spiraling inward, regardless of how long it stays there. This idea may seem arbitrary from a classical standpoint, but it aligns perfectly with experimental evidence. The lowest allowed energy state plays a crucial role in this explanation. There exists a minimum energy that an electron can have within an atom. It cannot lose energy beyond this point. Once the electron occupies this lowest state, there is nowhere further down to go. No transition is possible, and therefore no radiation occurs. The atom reaches a condition of absolute stability. This concept of a lowest allowed state has no counterpart in classical physics, where energy can, in principle, decrease without limit. This minimum energy state explains why electrons do not collapse into the nucleus. Classical reasoning assumes that electrons can always move closer, always lose a bit more energy. The quantized picture forbids this. The electron cannot occupy states between allowed levels, and it cannot exist at the nucleus itself. The stability of matter is thus guaranteed by the existence of forbidden states just as much as allowed ones. Another important aspect of stability lies in the discrete nature of energy exchange. Energy is not lost continuously, but only in exact amounts corresponding to differences between allowed states. If an electron is already in the lowest state, no such difference exists. Radiation becomes impossible, not unlikely. This distinction is critical. Atomic stability is not statistical or approximate, it is exact. This new understanding of stability also resolved the apparent conflict between atomic behavior and electromagnetic theory. Classical electrodynamics remains valid for radiation processes, but only when transitions occur. While an electron remains in a stable state, classical radiation laws simply do not apply. The atom operates under a special set of rules that override classical expectations at microscopic scales. This selective validity of physical laws was a revolutionary idea. Stability also acquired a new meaning. In classical systems, stability often results from equilibrium, where opposing forces cancel each other. In atoms, forces do not cancel. The electric attraction between the electron and nucleus remains strong. Stability arises not because forces vanish, but because motion is constrained. The electron is allowed to exist only in states where radiation does not occur. Stability is therefore not mechanical balance, but rule-based permission. This shift had profound implications. It meant that stability could not be understood solely in terms of forces and motion. Instead, it required understanding the structure of allowed states. This idea would later become central to quantum mechanics, where stability is explained through wave functions, boundary conditions, and energy eigenvalues. The early atomic model provided the first glimpse of this deeper framework. The stability of atoms also explained the stability of chemical elements. Each element has a characteristic ground state configuration for its electrons. Chemical reactions involve rearranging electrons between atoms, but the electrons always end up in allowed states. They never fall endlessly toward nuclei. The quantized structure of atomic states thus underpins the entire periodic table and the consistency of chemical behavior. This explanation of stability was not merely theoretical. It was supported by precise agreement with observed atomic sizes. The radius of the hydrogen atom, calculated from the allowed states, matched experimental values. This showed that stability is not an abstract concept, but a measurable physical reality emerging from quantized rules. At the same time, this understanding exposed the limits of classical intuition. The idea that an electron can orbit a nucleus forever without radiating energy contradicts everything learned from macroscopic experience. Yet the atom is not a miniature version of the solar system. It belongs to a different domain where new principles apply. Accepting this required a profound shift in how physicists thought about nature. The stability of atoms thus became one of the strongest arguments for the quantum view of the world. It showed that matter exists not because classical laws are approximately correct, but because they are fundamentally incomplete. Atomic stability is not an accident, it is a consequence of deep constraints built into the fabric of reality. In resolving the question of why electrons do not collapse into the nucleus, physics gained more than a solution to a single problem. It gained a new way of thinking about what it means for something to exist over time. Stability was no longer explained by continuous motion and balance, but by discrete structure and forbidden possibilities. This insight laid the foundation for modern physics and revealed that the enduring solidity of the world rests on rules that are invisible, abstract, and profoundly non-classical. One of the most transformative ideas to emerge from early atomic theory was the precise connection between energy and light. Before this insight, light was understood mainly as a continuous wave that could vary smoothly in intensity and frequency. Classical physics treated energy and frequency as related but not fundamentally constrained. The atomic view changed this completely by revealing that light carries energy in exact amounts tied directly to its frequency. This relationship was not a convenience of theory, it was a rule imposed by nature itself. When an atom emits or absorbs light, it does so in a highly specific way. The energy involved in this interaction is not arbitrary. It is fixed by the difference between two allowed internal states of the atom. The light associated with this change has a frequency that is strictly determined by that energy difference. Higher energy changes produce higher frequency light, while lower energy changes produce lower frequency light. There is no flexibility in this relationship. Energy and frequency are locked together. This understanding resolved a long-standing mystery about why different colors of light behave differently. In classical theory, intensity was often treated as the main carrier of energy. Brighter light meant more energy, regardless of color. Atomic experiments showed something very different. Even very intense low-frequency light could fail to produce certain effects, while faint high-frequency light could trigger them instantly. This contradiction made sense only once energy was recognized as being proportional to frequency, not just brightness. In atomic processes, brightness reflects how many light quanta are involved, not how much energy each one carries. A single quantum of high-frequency light can carry more energy than many quanta of low-frequency light. This distinction is essential for understanding how atoms interact with radiation. An atom cannot absorb just any light by increasing intensity. It must receive light of the correct frequency to match an internal energy change. This frequency-energy link explained why atomic absorption is selective. An atom exposed to a broad range of light frequencies will ignore most of them. Only those frequencies that correspond exactly to allowed energy differences can be absorbed. When absorption occurs, the atom gains a precise amount of energy and moves to a higher internal state. Light of any other frequency passes through unaffected, no matter how strong it is. Emission follows the same rule in reverse. When an atom releases energy, it does not choose the frequency of emitted light arbitrarily. The frequency is dictated by the internal energy change. This is why atomic emission lines are so precise and reproducible. Each line represents a specific energy difference translated directly into a frequency of light. The spectrum becomes a map of atomic energy structure written in color. This relationship also unified previously separate areas of physics. Atomic structure, radiation, and spectroscopy became parts of a single coherent framework. Light was no longer an external phenomenon acting on atoms from the outside. It became a direct expression of atomic change. Every photon emitted or absorbed was a record of an internal rearrangement of energy. The precision of this connection had profound implications for measurement. Because frequency can be measured with extraordinary accuracy, energy differences within atoms could be determined with equal precision. This allowed scientists to probe atomic structure indirectly but reliably. Even without seeing inside an atom, its internal energies could be mapped by studying the light it emitted or absorbed. This link also reinforced the idea that atomic processes are discrete. Energy changes occur in steps, and each step corresponds to a specific frequency. There is no gradual sliding from one color to another within a single transition. This discreteness was a clear departure from classical expectations and further evidence that atomic behavior follows its own rules. The energy-frequency relationship also clarified why atomic radiation is stable over time. The frequencies of emitted light do not drift or blur because the energy differences between states are fixed. This stability is what allows atomic clocks and precise spectroscopic standards to exist. The regularity of atomic transitions provides one of the most reliable timekeeping mechanisms known. Beyond atoms, this principle influenced the understanding of light itself. Light could no longer be described solely as a wave spreading continuously through space. Its interaction with matter revealed a particle-like aspect where energy comes in indivisible units tied to frequency. This dual character of light, wave, like in propagation, and particle, like in interaction, became a defining feature of modern physics. The connection between energy and frequency also reshaped the concept of cause and effect in radiation. In classical thinking, radiation was caused by motion. In atomic thinking, radiation was caused by change of state. The frequency of light was not determined by how an electron moved, but by where it started and where it ended. This shift removed the need to describe detailed motion during emission and replaced it with a state-based description. This idea proved to be remarkably powerful in general. It applied not only to visible light, but to all forms of electromagnetic radiation, from radio waves to gamma rays. The same rule linked low-energy transitions to long wavelengths and high-energy transitions to short wavelengths. The entire electromagnetic spectrum could be understood as a scale of energy changes expressed through frequency. The broader impact of this insight extended into technology and everyday life. Devices such as lasers rely on controlled atomic transitions that produce light of a single precise frequency. Medical imaging, telecommunications, and quantum electronics all depend on the exact relationship between energy and frequency first revealed through atomic behavior. At a deeper level, this principle changed how physicists thought about explanation. Instead of asking how light is produced mechanically, they asked what energy changes are allowed. Once those were known, the properties of light followed automatically. This reversal of thinking placed structure and rules ahead of motion and mechanism. The strict link between energy and frequency also hinted at deeper constraints in nature. It suggested that information, energy, and radiation are intertwined. A photon carries not just energy, but information about the system that emitted it. By measuring its frequency, one learns about the internal structure of the source. In the end, the connection between energy and frequency revealed a hidden order beneath the apparent diversity of light. Colors were no longer just sensory experiences but precise indicators of energy change. Light became a language spoken by atoms, with frequency as its grammar. This insight completed a crucial part of the atomic picture. It showed that matter and radiation are not separate realms but deeply connected aspects of a single physical reality. The atom does not merely interact with light, it defines light through its own structure. By uncovering this relationship, physics gained a unifying principle that continues to shape our understanding of the universe at its most fundamental level. No scientific model, no matter how successful, escapes its limitations, and the early atomic picture was no exception. While the new description of atomic structure solved some of the most pressing problems in physics, it also revealed its own boundaries. These limitations were not signs of failure, but indicators of how far understanding had progressed and where deeper insight was needed. By recognizing both what the model explained and what it could not, physicists were guided toward the next stage of discovery. The most obvious restriction appeared when attention shifted beyond the simplest atom. Hydrogen, with its single electron, fit the model beautifully. Calculations matched observations with striking accuracy. However, when scientists attempted to apply the same framework to atoms containing more electrons, the simplicity quickly disappeared. The interactions between multiple electrons introduced complexities that the original picture could not handle. The predicted energies no longer matched observed spectra, and new patterns emerged that resisted explanation. These difficulties revealed that treating electrons as independent particles moving in fixed paths around the nucleus was an oversimplification. In multi-electron atoms, electrons influence one another through their electric charges. Their motions are coupled, and their energies depend on collective behavior rather than isolated orbits. The early model lacked the tools to describe these interactions accurately, highlighting the need for a more comprehensive theory. Another limitation lay in the inability to explain fine details observed in spectral lines. High-resolution measurements revealed subtle splittings and shifts that could not be accounted for by simple energy level calculations. External influences, such as magnetic and electric fields, caused additional effects that the basic model could only describe qualitatively, if at all. These phenomena hinted at deeper internal structures and symmetries not captured by the initial assumptions. Relativistic effects also exposed shortcomings. As experimental precision increased, small deviations from predicted values became noticeable, especially in systems involving higher energies or heavier nuclei. These discrepancies pointed to the influence of relativistic corrections, which were beyond the scope of the original framework. The need to incorporate both quantum ideas and relativity became increasingly apparent. Perhaps the most significant conceptual limitation was the reliance on classical imagery. The picture of electrons following defined paths around the nucleus was useful pedagogically, but misleading physically. No experiment could observe such paths, and attempts to interpret them literally led to contradictions. The model worked not because electrons truly moved like planets, but because the mathematical structure captured key aspects of energy quantization. This realization forced physicists to confront an uncomfortable truth. Some elements of the model were not meant to represent reality directly, but served as symbolic tools. The distinction between a model that predicts correctly and one that describes what truly exists became increasingly important. This shift in thinking marked a turning point in scientific philosophy. The inability to describe how transitions actually occur was another limitation. While the model specified the energy differences involved, it offered no account of the process connecting initial and final states. The transition itself was left unexplained, treated as an instantaneous event without internal dynamics. This gap underscored the incompleteness of the description and motivated the search for a theory capable of handling change more fundamentally. As these issues accumulated, it became clear that a new language was required. The concepts of position and trajectory, inherited from classical mechanics, were no longer adequate. Physicists began to explore alternative descriptions based on waves, probabilities, and mathematical operators. These approaches aimed to retain the successful predictions of the early model while providing a deeper and more consistent foundation. Despite its limitations, the model achieved something remarkable. It demonstrated that quantization was essential and non-negotiable. Any future theory would have to preserve the discrete nature of energy levels and the connection between these levels and observed spectra. In this sense, the early atomic picture set the constraints within which all later theories would operate. The limitations also highlighted the importance of experimental guidance. Each discrepancy between prediction and observation served as a clue, rather than a failure. The model's breakdown in certain regimes pointed directly to the phenomena that required further explanation. This interplay between theory and experiment drove rapid progress and refinement. The recognition of these shortcomings did not diminish the model's historical importance. On the contrary, it underscored its role as a bridge between classical and quantum thinking. It provided a concrete example of how classical concepts could be partially retained while being fundamentally reinterpreted. This transitional role was essential in helping physicists adjust to a radically new worldview. As more sophisticated theories emerged, many of the early model's features were replaced or redefined. Orbits gave way to probability distributions. Definite paths were replaced by wave-like behavior, yet the core insights survived. Energy quantization, discrete states, and transition-based radiation remained central pillars of atomic theory. The process of moving beyond the initial model illustrates a broader pattern in scientific development. Progress often occurs through models that are known to be incomplete, but are nevertheless profoundly useful. Such models capture essential features of reality while leaving room for deeper understanding. Their limitations are not weaknesses but guides. In retrospect, the early atomic picture can be seen as a necessary step rather than a final destination. It clarified what needed to be explained and eliminated possibilities that no longer fit the evidence. By doing so, it narrowed the path forward and made subsequent breakthroughs possible. The eventual development of full quantum mechanics did not erase the achievements of this earlier work. Instead, it absorbed and extended them. The limitations that once seemed problematic became sources of insight, revealing the need for new principles and new mathematical structures. Through this process, physics learned an important lesson about the nature of explanation. A model can be true in its predictions without being literally true in its imagery. Understanding lies not in clinging to pictures, but in grasping the underlying relationships that govern observable phenomena. The early atomic model, with all its successes and shortcomings, thus occupies a central place in the history of science. It marked the point at which classical intuition finally gave way to a deeper, more abstract understanding of nature. By revealing both the power and the limits of simplified descriptions, it opened the door to a richer and more accurate view of the atomic world. The influence of Niels Bohr's work extended far beyond the immediate explanation of atomic structure and spectra. Its deepest significance lies in how it reshaped the foundations of modern physics and altered the way scientists think about reality itself. What began as an attempt to resolve specific contradictions in atomic theory grew into a lasting framework that guided the development of quantum mechanics and transformed scientific philosophy. One of the most enduring contributions was the introduction of a new attitude toward physical laws. Bohr showed that laws previously considered universal could have limited domains of validity. Classical mechanics and electrodynamics were not wrong, but incomplete. They worked extremely well at large scales and low energies, yet failed at the atomic level. This realization changed how physicists evaluated theories. A theory was no longer expected to explain everything everywhere, but to work accurately within a defined range of conditions. This shift had profound consequences for theory building. Instead of forcing nature to fit established concepts, physicists learned to let experimental results dictate new principles. Bohr's willingness to abandon classical continuity in favor of discrete states set a precedent for accepting counterintuitive ideas when evidence demanded them. This pragmatic approach became a hallmark of modern physics. Another lasting impact was the emphasis on the role of measurement and observation. Atomic behavior could not be fully described without considering how systems interact with measuring devices. Energy levels, transitions, and radiation all became meaningful only through observable outcomes. This focus on what can be measured, rather than on speculative mechanisms, influenced the development of quantum mechanics and its interpretation. Bohr also played a central role in shaping the philosophical understanding of quantum theory. He argued that classical concepts such as position and momentum cannot always be applied simultaneously at the atomic scale. Instead of rejecting these concepts outright, he proposed that they are complementary. Each provides valid information in certain experimental contexts, but no single picture captures the whole reality. This idea challenged the notion that a complete description must be unified and intuitive. The principle of complementarity had implications far beyond atomic physics. It suggested that nature may require multiple, mutually exclusive descriptions to be fully understood. This idea influenced debates about determinism, realism, and the nature of scientific explanation. It encouraged scientists to accept ambiguity and limitation as fundamental features of knowledge rather than temporary shortcomings. Bohr's work also helped establish the central role of probability in physics. While classical theories sought exact predictions, atomic behavior demanded statistical descriptions. The outcomes of individual events could not be predicted with certainty, only the probabilities of different outcomes. This acceptance of fundamental uncertainty marked a decisive break from centuries of deterministic thinking. In practical terms, Bohr's ideas laid the groundwork for countless technological advances. The understanding of atomic energy levels and transitions is essential to lasers, semiconductors, and modern electronics. These technologies depend on precise control of quantum states, a direct descendant of the atomic principles first articulated in early quantum theory. The influence extended into chemistry and materials science. The structure of the periodic table, the nature of chemical bonds, and the behavior of solids all rely on quantum principles rooted in atomic theory. By explaining why electrons occupy specific states, Bohr's work provided the conceptual foundation for understanding why matter has the properties it does. Bohr's legacy is also evident in the collaborative culture of modern physics. He fostered an environment where open discussion, debate, and critical thinking were encouraged. His institute became a center for the exchange of ideas, shaping generations of physicists. This emphasis on dialogue and interpretation helped physics navigate the conceptual challenges posed by quantum theory. Perhaps the most profound impact of Bohr's work lies in its challenge to classical realism. The idea that physical properties exist independently of observation became difficult to sustain at the atomic level. Instead, properties such as energy and position acquired meaning only within specific experimental contexts. This shift reshaped philosophical debates about the nature of reality and knowledge. Bohr did not claim to provide final answers to these questions. Instead, he emphasized the limits of what can be known and described. This humility became a defining feature of quantum theory. Rather than offering a single, complete picture of reality, the theory provided a set of rules for predicting outcomes and understanding relationships between observations. The lasting influence of Bohr's ideas can be seen in how modern physics approaches new frontiers. Whether in particle physics, cosmology, or quantum information, scientists remain cautious about extending familiar concepts beyond their tested domains. The lesson learned from atomic theory, that nature may defy intuition at extreme scales, continues to guide exploration. Bohr's work also demonstrated the power of simple principles. A small number of bold assumptions led to a dramatic expansion of understanding. This showed that progress does not always come from increasing complexity, but from identifying the right constraints. By focusing on what is allowed and forbidden, physics uncovered a deeper order underlying apparent chaos. The historical significance of this contribution lies in its role as a turning point. It marked the transition from classical to quantum thinking and set the stage for a century of discovery. Without this shift, many of the most important advances in science and technology would not have been possible. In the broader context of human knowledge, Bohr's legacy reminds us that understanding is an evolving process. Each generation inherits concepts that work within certain limits and must be prepared to revise them when new evidence appears. This dynamic view of knowledge is one of the most valuable lessons of modern science. The explanation of atomic structure did more than solve a scientific puzzle. It changed how humanity understands the relationship between theory, observation, and reality. It revealed that the universe is governed by principles that may resist simple visualization, yet yield precise and reliable predictions. In the end, the lasting impact of this work is not confined to physics textbooks or laboratories. It lies in the mindset it fostered, a willingness to question assumptions, accept uncertainty, and embrace abstraction in the pursuit of truth. Through this legacy, the insights born from the study of the atom continue to shape our understanding of the world and our place within it.